You know that moment, that feeling you get when you're on the phone with tech support, maybe trying to get your internet back online?
Oh, yeah, I know it well.
And the person on the other end, super helpful, says, okay, now, on your modem, can you see the little blinking light? Or could you please go into your phone settings and turn Wi-Fi off and on again?
Absolutely. You're the one actually doing the thing, pushing the button, flipping the switch on your end.
Exactly. You're not just describing the problem, you're like actively involved in fixing it. You're using your device, your tools, based on what they're telling you.
You're an active participant, not just a passive observer giving information.
Right. And that got me thinking, what happens when that helpful voice isn't, another person, but an AI? We hear so much about AI agents doing things for us, booking trips, analyzing data.
Stuff they can do entirely on their own, using their own digital tools.
Yeah. But what about these situations where the AI actually needs us to do something, where it has to guide us, the users, through steps using the things we have access to?
Well, that's a really critical piece of the puzzle for making AI truly useful in the real world.
Yeah.
And honestly, it's been kind of overlooked in a lot of the ways we test these AI agents.
So it's the difference between an AI talking at you versus an AI really working with you.
Precisely. It's about collaboration in a shared space where both the AI and the human can take actions.
And that exact dynamic, this idea of dual control, where both the AI and the user have tools and can change things, that's what we're digging into today. We came across this really fascinating new research paper.
Yes, it introduces something called two-bench. That's tau squared bench. It's basically a new testing ground, a benchmark, designed specifically to see how well AI conversational agents handle these situations where they need to collaborate with a human user who can also act.
So our mission for this deep dive is to really unpack two-bench. Why was something like this needed? How did they even build it? And maybe most importantly, what did they find out when they tested today's big AI models? How good are they really at guiding you?
Yeah, the results are. Well, they're pretty revealing about where things stand. Let's get into it.
Okay, so maybe let's start with the why. What was the problem with how AI agents were being evaluated before this two-bench came along? The paper talks about single control environments.
Right. So think about most typical AI agent tests. The AI gets a task, maybe find me a cheap flight, or recommend a good sci-fi book.
Okay.
The AI has access to a bunch of tools, maybe an API for flight searches or a database of books. It uses these tools, does its thing, and gives you the answer.
So the AI is the only one really doing anything in the simulated world. It's using the tools, accessing the data.
Exactly. The user's role in these benchmarks is mostly just providing the initial request, maybe answering a few clarifying questions like what dates or what genre. You're essentially passive when it comes to the actual execution of the task.
You're not like interacting with the simulated airline website yourself or checking settings on a fake phone.
Precisely. Your interaction is mainly just the conversation. You might see the results of the AI's actions, but you're not performing actions in that shared environment yourself. The paper mentions Talbench, that's Talbench, the predecessor as an example, focusing on retail and airlines, where the user mainly just gives constraints.
But as we said with the tech support example, that's just not how a lot of real-world collaboration works, is it?
Not at all. Think about that mobile data issue again. The AI agent on the phone can check your account, maybe enable a feature on their end, but they need you to go into your phone's settings menu, maybe toggle airplane mode, check the signal bars, maybe even pop the SIM card out and put it back in.
Right. Things only I can do with my physical device.
Exactly. In those cases, the user is an active executor of instructions. You have your own tools, the settings menu, the physical buttons, the SIM card tray, and you have agency over your part of the environment. The task only gets solved if both sides do their part.
So the big missing piece in older benchmarks was testing the AI's ability to actually guide those user actions effectively, to coordinate with someone who also has tools and can change things.
That's the core gap two-bench aims to fill. The single control setups just don't capture that complex back-and-forth collaborative dynamic.
Which leads us directly to two-bench and this idea of a dual control world.
Yes, that's the central innovation here, creating an environment where both the AI agent and a simulated user can execute actions that affect a shared state.
Okay, dual control. Sounds like it means a pretty specific way to model how that interaction works. The paper mentions a formal model, decentralized, partially observable Markov decision process, DPOMDP.
Yes, it's a bit of a mouthful. DPOMDP. But it's actually a really powerful concept from AI research, perfect for these kinds of situations.
Okay, break it down. What does DPOMDP actually mean in this context?
All right, let's unpack it piece by piece. Decentralized means you have more than one independent decision maker or player. Here, it's the AI agent and the user simulator. They act separately.
Got it. Two players acting on their own.
Then, partially observable. This is super important. It means neither player has the full picture. They don't see everything about the environment state or necessarily everything the other player's doing or seeing.
Ah, okay. So the AI doesn't automatically know the exact signal strength on my phone, right? It relies on me checking and telling it, or it's seeing the result of an action I took.
Exactly. And you don't see the internal customer database the agent is looking at. Each has their own limited view. That's the partially observable part.
It makes sense. Feels more realistic. And the Markov decision process part.
That's the standard way in AI to model situations where an agent takes actions. Those actions change the state of the world according to certain probabilities, and the agent gets rewards based on the state it reaches. It's about modeling actions, state changes, and goals over time.
So putting it all together, DEC-POMDP is a formal way to describe this setup with two players, each with their own limited view, taking turns to act in a shared world to try and achieve some goal.
Precisely. And in two-bench, this world, the shared state space, includes everything relevant, the agent's database info, the user's simulated phone status, airplane mode on-off, data enabled, signal strength, etc., and even the history of the conversation itself.
So the world keeps changing based on what happens. And what can they actually do in this world, the actions?
That's the action spaces, AI. Each player has a set of actions they can take. Crucially, it's not just talking. They can either send a message or call one of their available tools. And importantly, only one player acts per turn, simulating a back-and-forth conversation.
And they each have different tools. Can you give examples from the telecom domain they built?
Sure. The AI agent might have tools like get customer by to look up account info or enable roaming to turn on roaming service from their end.
Okay, stuff the company controls.
Right. And the user operating their simulated phone has tools like toggle airplane mode, check network status, maybe reseat SIM card, or toggle data, things you'd actually do on your phone.
So the user isn't just typing responses. They can trigger these simulated actions on their device. What happens after an action? How do they know what happened?
They get an observation. Or if you call a tool, your observation might be the tool's output, like the network status after you check it. If the other player sends a message, your observation is that message. But again, it's partial. You don't see the internal workings of the other player's action, just the observable outcome or message.
Gotcha. And the transition function, T, that sounds like how the world changes.
Exactly. It defines how the shared state updates based on the action taken. And this is where dual control really matters. An agent action like enable roaming changes the state in the CRM part of the world. A user action like toggle airplane mode changes the state of the simulated phone part of the world. Both players' actions modify the shared reality.
So my actions matter just as much as the AI's for changing the situation. How do they know if they actually solve the problem?
That's the reward function.
Yeah.
It's basically a score given at the end, based on the final state of the world. Did the user's mobile data start working? Is the phone connected? The reward function checks the final state of, say, the user's device simulation to see if the initial issue is resolved. High reward means success.
And lastly, the instruction space.
That just sets up the specific scenario, what problem the user starts with, what their goal is, and any specific rules or policies the agent needs to follow for that domain.
Okay, so this DEC-POMDP framework lets them formally model these back-and-forth collaborative interactions where both the AI and user can talk and act, impacting the shared, partially visible world. It really sets the stage for testing coordination and communication in a way older models couldn't.
Precisely. It shifts the challenge from just solving a problem autonomously to effectively guiding a partner through their necessary actions.
All right, so that's the theoretical underpinning. How did they actually build this toe bench? The paper mentions 4 main contributions. Let's start with the first, this new telecom domain.
Right, they realized they needed a domain where this dual control dynamic felt natural and necessary. Telecom technical support turned out to be a perfect fit.
Why telecom specifically?
Because troubleshooting phone issues almost always requires actions from both sides. The support agent needs to check account settings, network status on their end, maybe push an update. But you, the user, have to interact with your physical phone, check settings, reboot it, toggle modes, maybe even physically handle the SIM card.
Yeah, you can't fix my phone signal just by clicking buttons in your office. I have to do stuff here.
Exactly. So they built this simulated world with two main parts. The agent side, representing a customer relationship management (CRM) system with customer profiles, line status, service info, and the user side, simulating a phone's state signal, battery, settings like airplane mode, mobile data, MMS configurations.
And each side gets its own toolkit, like we discussed. Agent tools like check service status, user tools like toggle airplane mode or check network status.
Yes, and figure 2 in the paper shows a great example. The agent uses a tool to enable roaming, but that's not enough. The agent then needs to guide the user to use their tool, coddle data, to make sure mobile data is actually switched on the phone. Both actions are required for the user's data to work while roaming. That interdependence is key.
That really clarifies the dual control aspect. Okay, so a well-suited domain, what was the second contribution? It sounds like creating enough test scenarios could be a huge amount of work.
Ah, yes. Manually writing thousands of unique tech support dialogues would be incredibly time-consuming and hard to manage. So they developed a clever compositional task generator.
Compositional, like building with blocks.
Exactly like that. Instead of writing whole scenarios, they defined smaller, fundamental units called atomic subtasks. Think of an atomic subtask as representing one specific, isolated issue.
Like what?
Like maybe airplane mode is accidentally on, or
Right.
SIM card is not seated correctly, or mobile data is toggled off on the phone, or roaming services disabled on the account. Just one specific thing that's wrong.
Okay, these basic problem units, how are they defined so a computer can use them?
Each atomic subtask is defined programmatically with three parts. One, initialization functions. These set up the problem state. So set airplane mode, true, would turn airplane mode on in the simulation at the start. Disable roaming service would switch it off in the agent's CRM state.
Got it, creates the starting problem.
Two, solution functions. These specify the tool calls needed to fix that specific atomic problem. Importantly, this might be an agent tool or a user tool. So for the airplane mode issue, the solution is the user's toggle airplane mode tool. For the roaming issue, it's the agent's enable roaming tool.
Okay, the fix for that specific block.
Three, assertion functions. These are checks performed at the end to verify if the subtask's specific problem has been resolved, like assert airplane mode, false, or assert service status, connected. They confirm the fix worked for that piece.
So setup, fix, check, define for each little atomic problem block. How does that help make bigger, more complex tasks?
They group these atomic subtasks logically. Then the generator programmatically selects and chains them together. So a complex task might involve, say, an initial state where airplane mode is on and roaming is disabled. The solution would require guiding the user to toggle airplane mode and the agent using its tool to enable roaming.
Ah, so you can combine these blocks to create scenarios with multiple steps and dependencies, involving actions from both sides.
Exactly. And you can control the complexity by choosing how many and which types of blocks to combine. The paper mentions their telecom domain has 114 tasks sampled this way, but the generator could potentially create over 2,200 combinations.
That's super efficient. And because it's programmatic, you get diversity, you know the correct solution steps in theory, and you have automatic checks, the assertions, to see if the final state is right.
Precisely. It gives them a large, varied, and verifiable set of test cases without manual authoring.
Okay, domain, task generator. What's the third key contribution? Something about the user simulator.
Yes, the reliable user simulator. This is absolutely critical for a dual control benchmark. If you're testing how well an AI guides a user, you need that simulated user to behave well, reliably.
Why is that so tricky? Can't you just use another AI to pretend to be the user?
You can, and they do use an LLM like GPT 4.1 for the user sim. But the danger is if the user sim misunderstands instructions often, or says it did something it didn't, or just generally messes up using its tools.
Then you don't know if the main AI failed because it made a mistake or because the user sim was just being difficult or buggy.
Exactly. It introduces noise and makes it hard to evaluate the actual agent you care about. So 2inch tackles this by tightly coupling the user simulator LLM to the environment.
Tightly coupling, what does that mean?
It means the user sim isn't just generating text responses based on the conversation history. When the main agent instructs it, say, please toggle airplane mode, the user sim's goal is constrained to output the actual tool call, like toggle airplane mode, if it understands and the tool's available.
Ah, so it tries to translate the instruction into an executable action.
Yes, and then the environment executes that tool call. The user sim then observes The actual result from the environment, like the state change, or tool output, not just text it imagines, it's grounded in the simulation's reality.
So its understanding and actions are directly linked to the simulated world state and tools, not just free-form text generation.
Correct. It makes the user sim behave much more consistently, according to the rules of the simulation. And the results show this works. They report much lower error rates for the user sim in this new telecom domain, only 16% total errors, and just 6% critical errors that stop the task.
Wow, compared to what?
Compared to the user sims in the older bench domains, which apparently had error rates around 40–47% with 12–13% critical errors.
Okay, that's a huge improvement in reliability. Getting the user sim errors down that much means you can be much more confident that when the main agent fails, it's actually the agent's fault.
Exactly. It cleans up the evaluation signal significantly.
Makes sense. So domain, task generator, reliable user sim. What's the fourth contribution? Something about diagnosing failures.
Right. Fine-grained diagnosis of agent failures. They didn't just want to know if agents failed, but why. So they set up different ways to run the tests.
Different modes.
Two main ones plus an extra. The first is no user mode. Here, the AI agent gets the problem description, but it's giving control of all the tools its own and the user's tools. There's no separate user sim involved.
Oh, so the agent just does everything itself, uses its CRM tools, and simulates toggling airplane mode on the user's behalf.
Exactly. This isolates the agent's pure reasoning and planning ability.
Yep.
Can it figure out the correct sequence of all necessary steps, even the user steps, if it doesn't have to communicate or coordinate?
Okay, strips away the interaction challenge. What's the main mode then?
That's default mode. This is the full dual control setup. The agent only has its tools. It has to talk to the user simulator, understand the problem, figure out a plan, instruct the user sim to use its tools, process the responses, track the state, the whole 9 yards.
So no user tests reasoning alone. Default tests reasoning plus communication and coordination with the active user sim.
Precisely the distinction. By comparing performance between no user and default modes on the same tasks, you can see how much performance drops just because of the interaction burden. If there's a big drop, the interaction is the main problem.
That's a really smart way to diagnose the bottleneck. Do they have any other modes?
They also used an Oracle plan mode. Here, the agent is given the perfect, complete sequence of tool calls, both agent and user tools, needed to solve the task.
So it doesn't even need to figure out the plan, just execute it.
Right. This tests its ability to simply follow a known good plan, turn by turn, coordinating with the user sim. Comparing default to Oracle plan helps isolate how much of the difficulty comes from the planning part itself versus the execution and interaction part.
Okay, so these different modes let them really pinpoint whether failures are due to bad planning, bad communication coordination, or both. Very thorough.
It provides a much deeper understanding than just a single pass-fail score.
All right, we've got the setup. The problem, the benchmarks design, the domain, the task generation, the user sim, the diagnostic modes. Now for the big reveal. What actually happened when they tested current large language models on 2Bench?
Well, the headline finding is pretty clear. This new telecom dual control domain is significantly harder for these state-of-the-art LLMs than the older single control benchmarks they often do well on.
How much harder are we talking?
We're talking a big drop. Take a strong model like GPT 4.1. In the older retail and airline domains from Bench, its success rate called pass at 1, solving it on the first try was around 74% and 56% respectively. Pretty good.
Yeah, solving more than half.
On this new telecom dual control domain, its pass at 1 score plummets to just 34%.
Wow, from over 70% down to basically 1/3 success. That's huge.
It is. And other models they tested, like newer GPT variants or Claude Sonnet, showed similar steep declines. Even allowing multiple attempts, pass at K, the success rates on telecom lag way behind the older benchmarks. This new setup is definitely hitting a weak spot.
Okay, so what is that weak spot? Did the diagnostic modes help figure that out?
Absolutely. The comparison between no user mode and default mode is incredibly revealing. This is shown really clearly in Figure 4 of the paper.
Right, no user is the AI doing everything itself. Default is AI guiding the user sim.
Exactly. And the performance difference is stark. For GPT 4.1, we saw it got 52% pass at 1 in no user mode. So reasonably capable of figuring out the steps if it controls everything.
Okay, over half the time it knows the solution path.
But switch to default mode, where it has to guide the user sim. Success drops to 34%. That's an 18 percentage point penalty just for adding the interaction layer.
18 points lost just because it has to communicate and coordinate.
And for another model, a 4 mini, The drop was even bigger, from 67% no user down to 42% in default, a massive 25-point difference.
Okay, so let's really process that. The AIs are actually pretty decent, often better than 50-50, at figuring out the technical steps needed if they can just execute them. But the moment they have to explain those steps, get a separate user, even a simulated one, to perform some of them, and manage that back and forth, their ability to successfully complete the task just tanks.
It strongly points to the communication, coordination, instruction following, and state tracking involved in guiding another agent as being the primary bottleneck, potentially even more so than the core reasoning or planning ability itself for these kinds of tasks.
It's the working with you part that's really, really hard for them right now.
It seems so. The complexity of managing that interaction reliably seems to be a major hurdle. Even the Oracle plan results hint at this.
How so? That's where they get the perfect plan, right?
Right. Giving them the perfect plan does boost performance significantly compared to default mode. GPT 4.1 jumps to 73% in Oracle plan. So planning is definitely part of the challenge.
But it's still not 100% even with the perfect plan.
Exactly. Even knowing the perfect steps, the agent still sometimes fails when interacting with the user sim in Oracle plan mode. This suggests there's inherent difficulty just in the turn-by-turn execution and coordination, separate from figuring out the plan itself.
So planning is hard, but guiding the execution with a partner is also hard, and maybe even harder.
Yeah.
Fascinating. Did they find anything else? What about that workflow document idea?
Yeah, they tried giving the agents a more detailed, structured, workflow-based policy document.
Cool.
It gave a small boost in default and no user modes, suggesting better guidance can help a bit with both reasoning and interaction.
Okay, makes sense.
But, kind of weirdly, it actually hurt performance in Oracle plan mode.
Wait, giving it more info made it worse when it already had the perfect plan? How does that work?
The authors guess that maybe having both the perfect Oracle plan and this separate detailed workflow document might have confused the agent. Like, it struggled to reconcile the two, making it harder to just execute the simple plan it was given.
Huh. So sometimes more information isn't better, it can just muddy the waters for the AI. Interesting. What about the tasks themselves? Did harder tasks lead to lower scores?
Definitely. Figure 5 shows a clear trend. Performance goes down as tasks get longer, require more actions or turns, or combine more atomic subtasks. Agents really struggled in default mode on tasks needing more than, say, 7 actions.
More steps, more chances for things to go wrong in the communication loop, I guess.
Seems likely. The gap between no user autonomous and default collaborative modes stayed pretty consistent even for longer tasks, again suggesting the communication overhead is a persistent drag. Although the gap narrowed just a tiny bit for the very longest tasks, maybe hinting that super long-range planning is hard even when autonomous.
Okay, so length matters. What about the type of problem? Like, is fixing a basic connection easier than fixing, say, MMS messaging?
Yes, Figure 6 shows that clearly. They categorized issues by complexity. Basic service issue, then mobile day issue, which might depend on service being okay first, then MEP issue, which might depend on both service and data.
A kind of dependency chain.
Exactly. And the agents performed much worse on the more complex types, like mobile data and MMS issues, compared to the simpler service issues. This highlights struggles with multi-stage reasoning and handling those dependencies, especially when trying to guide a user through that complex flow.
So it's not just the number of steps, but the logical complexity in needing to solve prerequisite problems first. And finally, maybe the most intriguing part, what about the user? Did the simulated user's personality matter?
Hugely.
Yeah.
This is shown in Figure 7, and it's really insightful. They tested the agents against different user simulator personas. An easy persona, simulated to be tech-savvy, asks good questions, follows instructions well. And a hard persona, simulated to be less tech-savvy, easily confused or flustered.
Oh, wow. And did it make a difference?
A big difference. Agents perform significantly better with the easy user sim than the hard one.
That feels so intuitive. It's always easier to help someone with tech problems if they kind of know what you're talking about.
Absolutely. And interestingly, the none persona, where the user sim had no specific instructions, performed more like the hard persona, sometimes even slightly worse.
So the default isn't necessarily an easy collaborator.
Apparently not. This really hammers home how crucial it is for these AI agents to be able to adapt their communication style and instructions based on the user's likely level of understanding and ability to follow along. Success isn't just about the AI's knowledge. It heavily depends on the user's ability to participate effectively and the AI's ability to enable that participation.
Okay, let's try to wrap up the key findings then. This new telecom dual control setup in the two-bench is way harder for current LLMs. The biggest hurdle seems to be the communication and coordination needed to guide an active user, much more so than just figuring out the solution steps autonomously. Task complexity, both length and logical dependencies, makes it even harder. And crucially, the AI success really depends on how easy the user is to work with, highlighting a major need for adaptability.
That's a great summary. It paints a picture of AI that's getting good at autonomous problem solving in some areas, but still has a long way to go when it comes to effective, robust collaboration and guidance with humans in shared environments.
So let's talk about the so what. Why does this research, these findings from two-bench, really matter for AI out there in the real world?
Well, the most direct implication is for customer support, especially technical support. Companies are definitely looking at using AI agents for this, but this research shows we need benchmarks like two-benchmark to actually test if an AI can handle the collaborative part, guiding a real user through steps on their own device, not just answer questions.
Right, because that guidance part is non-negotiable in many support scenarios.
Absolutely.
Right.
But it goes way beyond tech support. Think about any situation where an AI needs to work with a person to get something done, and the person needs to perform actions.
Like what?
Maybe an AI guiding you through assembling furniture from instructions, or helping you configure a complex piece of software by telling you what menus to open and buttons to click on your screen, or a smart home AI helping you troubleshoot a connected device.
Or even like an educational tool where an AI guides a student through an interactive science experiment simulation where the student controls parts of it.
Exactly. Any scenario involving collaborative task execution where the AI needs to instruct, clarify, and react to human actions in a shared environment.
So it touches on the fundamental ability of AI to be a useful partner, not just a tool that operates in isolation.
Precisely. And that ties into responsible AI deployment. If we're putting AI agents into roles where they interact closely with people, especially people with varying levels of technical skill, we need to know they can handle that interaction safely and effectively. Two-bench tests a critical part of that. Can the AI guide reliably without causing confusion or frustration?
The paper also mentions some areas where more research is needed based on what they learned.
Yes, they point out a few key things. One is continuing to improve the reliability of these user simulators, especially making them work well across different types of domains, not just telecom.
Makes sense, the user sim quality is crucial.
Another big one is finding ways to automate the creation of these complex benchmark domains and tasks more easily. It still takes a lot of expert effort to build something like the telecom domain.
And connecting back to the user personas.
Yes, they specifically called out the need for future work on modeling the expert-novice gap. How can we build agents that are better at sensing a user's level of expertise and automatically adapting their language, explanations, and the level of detail in their instructions? That's directly tied to the easy versus hard persona finding and is vital for making these systems work for everyone.
You know, this whole deep dive into two-bench really shifts the focus, doesn't it? It suggests the next big leap for AI might not just be about raw intelligence or autonomous capability.
It seems like a huge part of it needs to be about becoming better collaborators, better partners for us humans in these messy shared environments where we both have things to do.
Which leads to a really interesting final thought. What does it actually mean for an AI to truly guide a human effectively?
Yeah, it's more than just spitting out instructions.
Yeah, right. How do you build systems that are patient, that can tell when you're confused, maybe rephrase things, offer encouragement, tolerate it when you inevitably click the wrong button or misunderstand a step?
And adapt its whole approach based on whether you seem like you know what you're doing or if you're completely lost, making it feel less like wrestling with a machine and more like getting help from someone who actually understands where you're coming from.
Exactly. Two-bench really throws down the gauntlet, showing that this collaborative intelligence, this ability to partner effectively with us and guide our actions patiently and adaptively, well, that's still very much a work in progress for AI.
And perhaps the key to unlocking its true potential in countless real-world applications might depend less on how well it can act alone and much more on how effectively it can learn to work with us.
A challenge that will definitely keep researchers busy and something we'll be keeping a close eye on.